All right, so this is the end of internship talk of Armel, who has been working with the Everest team for the past 3 months on generally improving, through various means, the trust that we currently put in our compilation toolchain. So as a quick background, we're trying to extract mTLS, our TLS library to C, and we have a whole new set of tools that allow us to generate C code from F-star, and one of the problems is we're currently putting too much trust in them. So Armel has been looking at various ways to reduce the amount of trust that we're putting in our tooling. He's worked with a bunch of people, Nick, Tahina, myself, and many others, and we've had a great time, so I very much look forward to his talk.
Okay, thanks. So yeah, hi. And I'm going to talk about what I did during this internship. And so as Jonathan mentioned, I worked on multiple things, but I think they can all be regrouped under the general motto of improving trust in the compilation process from S star to C. If you have any question during the talk, please interrupt me. And yeah, I'll start with a general overview of the context, the motivations, and the headlines of what I've been doing. So basically, F star is one programming language where people can write code and prove it correct. And one goal of the Everest project is to have a nice compilation process to C, and that is able to produce efficient and readable C code from F star programs. And so by readable, we mean close to what a human would write. And the current compilation pipeline can be illustrated by the following schema. I will not detail all of it, but basically, you can write program in F star, and some subset of F star is called lodestar. And if your programs lie in this subset after some rewriting, then you will be able to feed it to the KreMLin tool, which takes lambda lodestar program, compiles them to C star, an intermediate language that is closer to C and has an explicit notion of buffers and structs, and do some rewriting, and finally compile it to CLite, which is an intermediate language of compcert. And at this stage, the C code can be printed out and fed to a C compiler such as GCC Clang or compcert. And at the moment, KreMLin is part of the trusted computing base, which means we trust KreMLin for what it does. And KreMLin is, in fact, at the center of Tradeoff applying this compilation scheme, which is a trade-off between easy verification in lodestar and the amount of trust we put in KreMLin. One extreme for this trade-off will be that lodestar is all F star programs, and then people would write high-level perifunctional code in lodestar, which will be easy to verify, but then expect that KreMLin automatically compares it to efficient and readable C, which is not very realistic. Another extreme will be to have a deep embedding of all the C standard in lodestar, which would make KreMLin trivial, but which would make the verification very painful, because now the user would have to reason about all the subtleties of C semantics in lodestar and track the liveness and the mutation of its data. So obviously, the current design of lodestar lies somewhere in the middle. Lodestar includes some C-like constructs like buffers, which are modeled in F star against some model of the heap, and which is faithful to the C semantics. Their contents are re-reflected logically as sequences of their elements, and then to use them, people have to reason about the liveness of a buffer, which part have been modified, which part have not, and etc. And so, for example, on the left is a bit of lodestar code, which allocates a new buffer, and it is compiled by KreMLin to the C code on the right, which does the equivalent buffer allocation. Lodestar also includes some higher level constructs, for example, inductive data types, which are primitive notion in F star, and which are compiled by KreMLin to C and unions. And here KreMLin is trusted to implement a correct compilation scheme. Such data have value semantics and are therefore very easy to use. You can just have them around and not have to reason about their liveness, for example. As a drawback, performance is not very predictable because it also depends on the optimization performed by the C compiler on structs and unions. And so, for example, you can write on the left the following inductive definition and manipulate such the values of this inductive, and it will generate the following structs in C through KreMLin. And here you can see that KreMLin performs some a small optimization. It notices that there is only one case in the inductive, and then compile that to a flat struct. If there were multiple cases, then maybe there will be a union in the produced C code. So one thing we can do to greatly improve trust in the current pipeline is to just mechanically verify KreMLin, and then we have a mechanical proof of it, we can extract it, and then we have a verified KreMLin tool. So I did an initial experiment with a proof of a subset of KreMLin, but as we'll see, there's still a lot of work needed to be able to replace the current tool. And another approach where we can look at, and which is another part of the work I did, is try to move some of the work done by KreMLin to lodestar. And this gives us another point of in the design space, which has been concretized by the Everest library, which is an ongoing development by Tahina. And what Everest does is add more C-like level constructs in lodestar, such as nested, mutable structs, unions, and buffers. So basically, pick some aspects of the deep embedding we would like to have and model it in lodestar. It's still a corrective subset of C. We still do not want to have all of C semantics deep embedded in lodestar. So for example, C specifies that if you have several structs as part of a union, then the common prefixes, you can have common fields between the structs that will be preserved when switching the case of the union. And Everest doesn't attempt at modeling that by design. But still, it gives us more control, for example, on mutability patterns we can have, the layout of our data. We can have initialized data that we initialize progressively. And of course, it's harder to use than just plain inductive, for example. All in all, it's another tool that we can use when compiling F-star to C. And that's probably going to be useful in the ongoing work on compiling mid-TLS to C. It's probably not going to be used everywhere, but in the situations where performance is critical and we want to optimize some specific pattern. And so, for example, if we want to represent the points 3D structure we have earlier, we would write the following in using array struct, and we see that it's a bit more specific than the inductive definitions. We explicitly lay out the fields we want to have and their types, and yep, that gives us the code on the right. A bit more on array struct. It follows a general pattern used in other F-star libraries, where low-level data is represented in proofs as pure level values. So for example, the contents of buffers is reflected as pure sequences. Operations on machine integers are reflected as mathematical operations on NAT. And similarly, in array struct, structs and unions are reflected as dependent map, which are just maps where the type of the values depend on the keys. And so another part of the work I did here was explore these points of the design using array struct and have and have a case study on the form of a tagged union library built on top of a resurrect. Tagged unions are a bit more higher level primitive that we can implement on top of a resurrect and that can attempt at bridging the gap between the low-level resurrect constructs and higher-level constructs like inductives. And the goal we had with this experiment were first to evaluate resurrect itself for usability and verification performance and give it one client that uses the library, and then explore a bit the design space for resurrect-based library, which interface to give them, how to design them, how to make robust proofs, how to design, what interface to give so that clients of the library can also have devise robust proofs, which lemmas, states, so that automation is useful, this kind of thing. So yeah, that's it for the general context, and I'm going to talk a bit about first the experiment with a mechanized proof of KreMLin. So basically, KreMLin architecture is, as I showed earlier, and I was interested more in the first transformation path from lodestar to C-star, and we wanted to formalize that using the Lin proof assistant. To give some context, lodestar is a first-order expression-based language with a built-in notion of buffers and structs. So you have, for example, a sub-buffer operation. You can read the buffer, allocate a new buffer. And C-star is also a first-order statement-based with also a built-in notion of buffers and structs. And it has statements a bit more like in C, where you can dereference a pointer to a mem set. You have pointer addition, for example, to compute an offset in buffer. And following the existing paper proof, the proof of the translation is proved by simulation in the style of COMSOL, for example. It amounts to show that any execution of the compiled program corresponds to an execution in the source program. Compilation is given by two definitions which compile lodestar expression to C-star expressions or to C-star statements. And then the proof defines several semantic gadgets such as head evaluation of statements and back translations from C-star to lodestar. It defines, using these gadgets, it defines the relation between the source and the target. And then we have to show that this relation relates a source and the compilation of the source, and then is preserved by stepping, by evaluation steps. And basically, we did some of the work, but not everything. What's done is defining the syntax, semantics, translation, the semantic gadgets, and then prove most of the lemma relating source and its compilation. The main difficulties were first, well, maybe unsurprisingly, many more additional technical lemma were required compared to the paper proof, which require either a lot of manual work or good automation, specific automation. So for example, the translations and back translations are written as functions that are actually partial functions, so you need to justify everywhere where you use them that they are actually defined. And for example, the relation composes them, so you have extra steps of reasoning to do. And then I think it's fair to say that there is also some amount of engineering required in Lin to have a nice general purpose tactics and automation still. So I worked with Leo a bit, and it was really responsive, and it was nice being part of the loop when I did in new features. But just to say that this experiment was also a process of understanding Lin and understanding what I needed and maybe what needed to be added. So yeah, this experiment still had interesting side effects, apart from averaging the amount of work that is needed to do. I found some minor bugs in the paper definitions and typos, which were fixed. And then it motivated the implementation of various new features in Lean, such as well-founded recursion, co-inductive predicates, and various improvements to the static framework. And as I said earlier, shifting perspective, another thing we can do is to add some trust to this compilation pipeline is just verify more things in lodestar. And this is what motivates this experiment of using RStruct to build a tagged union library on top of it. So to be more specific, a tagged union is basically equivalent to a non-recursive inductive data type. It's a data of C union and then some concrete tag, which represents in which case of the union we currently are. So for example, this is a tag union. It's a struct with a tag, which implicitly will only be 0 or 1, and then a union with 2 fields. And then the tag value describes in which field we are. So to express that as a library, first we define at the logical level a mapping between fields and tags. So what I mean with fields is that in RStruct, if you have, for example, a union with 2 fields A, B, then you have materialized in RStruct a list of fields as strings, field names. And similarly, a tag union is parameterized by a list of fields for the underlying union and a list of tags for this field. So this list of tags is provided by the user, which chooses how to tag the various fields. And then this list of tags as uint32s just has to be the same length as the list of fields, and the tags have to be unique. And given the data of the list of fields, the list of tags, we can define functions that map between a field and a tag and field. Then the library defines a well-formness invariant for tag unions, which takes a heap, a list of tags, and a pointer to some data in the heap, and then asserts whether the data in the heap actually corresponds to a valid tag union. It is left abstract in the interface, so the user never has to explicitly establish this invariant or destruct it. It's just threaded through the proof by using the provided constructions. But if you look at the definition, basically what it says is that first, the integer tag always has to be readable. Then the tag has to be a valid tag, so it has to be in the list of tags. And then the active field of the union has to match the tag, the integer tag that is in the struct. And that's it. In particular, that means that the actual data which is in the union can be anything. It can be uninitialized. It can be partially initialized. This invariant just says that it has to be in the right case. And then the library defines 4 operations. You can read a tag from a tag union, and it gives you a uint32. You can, given a pointer to a tag union and a field, you can have a pointer to the field into the tag union corresponding to the current data, the current case. And then you can either write directly given a field and a value, you can write them in the tag union, effectively changing the current field to be the field you gave. Or you can write a new tag, invalidating the data that was before. And this gives 2 patterns for changing the case of the union. The first one is more high level and more easy to use. And basically, you do a one-shot write that writes a new value for a case you give. you gave. It's easy to use, but it requires building the complete value, which may not be very idiomatic. If, for example, you have to construct a struct value just to write it. So in that case, you can also use a second pattern, which is more low level, where you can write a new tag. It invalidates the data, and then using the field operation, you can get a pointer to the data corresponding to that tag, and then perform some partial initialization like you do in C, for example, calling auxiliary functions that initialize progressively part of the structure. And both are supported by the library. And then this overall design generalized to other kinds of tag data. So for example, you can also think of a flat structure with some integer tags that indicate the validity of some of the fields. So for example, you would have a structure with some state, and then char data and the implicit invariant that this is only valid for some value of the state. And then another field is always valid, for example. And such patterns are interesting in the case where you have multiple fields that are shared between the cases, in which case this representation is more complex than 10 digits. Okay. And so one interesting aspect of this library is that it doesn't leak all the array construct to the user. You can just use 4 primitives and then the usual array operators to operate on the data that is stored inside, obviously. But it tries to be self-contained as much as possible. And then part of writing the library and evaluating whether it works well or not was trying to understand the performance both of array struct and the tag unit library itself. So I did the COBOL experiments, and first finding is that, well, one cause of bad performance can be caused by poorly formulated lemmas. So for example, this lemma from an old version of array struct. The problem here is a for row. Basically, instantiation of for row is implicit in Z3 and F star. So this will, if this lemma is around in the environment, it will get instantiated by some integer in the environment, and you have no way of controlling which one. So basically, it leads to proofs that are relatively fragile and may break in the future. And also, on a shorter term, it leads to unreplayable hints, where hints are a mechanism by F star that dumps the relevant parts of a proof to disk so that it can be replayed faster. But then the random things that may have triggered this lemma are not part of the hint base, and then the hints fail to replay, and you have to reprove everything again, which is slower. So the general thing you want to do here is put a pattern to guard the for that indicates to Z3 what terms to look for in the environment to insert for all. In that particular case, it was fixed by just putting this lemma abstract and then providing wrapper lemmas guarded by patterns. Another aspect of performance, which is not directly related to array struct, but okay. But yeah, but that I noticed using the Z3 profiler when trying to understand performance, is that we have our definitions for the bitewise operators are transparent, and they are modeled using bit vectors, which are effectively list of bits. And this is just a model that describes the behavior of the C operators, and it's erased when compiled to C. And essentially, these definitions would trigger a lot of list-related lemmas when it's not really relevant, going some slowdown. And it can be worthwhile to note that this can also be dangerous, because essentially this makes the model transparent to this tree. A model which may be too precise, so for example, define the operator for arguments where the C standard is not, says it's an indifferent behavior. And in that case, this tree will be able to sidestep the specification by using directly the model and manage to prove something that is incorrect and that will compile to an indifferent behavior. And I think JSON has an instance of that as a bug. So yeah, it's probably a good idea to just put this as abstract. And then finally, I try to investigate the performance of abstract on big structure with many fields, and it's constantly, it's currently not that great, because basically in abstract the representation of such a structure is a list of fields with types, and then there is a function that maps this representation to an actual star type, which is a dependent map. And when fed to this tree, I suspect this tree is often trying to just unfold these definitions walking on the list, which gets bigger and bigger with bigger struct. And this may motivate the use for the normalizer, which is a tool in F-star for metaprogramming, which essentially performs symbolic executions before sending the queries to this tree. And in that case, it will help generate the corresponding tag for these descriptions once and for all before sending everything to this tree. It's still an ongoing experiment because there are some bugs in F-star that needs to be fixed, but hopefully it will happen at some point. And then we can play some tricks and use the normalizer some more in the tag library itself to try to improve a bit the performance profile. Many operations in the library, namely field write and write tag, have to require or ensure that some tag matches some field. And this is expressed using the tag of field function that takes a field and returns the tag, and essentially works down the list of fields and tags and tries to find the field in the argument. And if we just feed that to this tree, then this tree has to compute that function. But in fact, the list of tags and the list of fields is non-statically, so we can just reduce this tag of field invocation upfront by using the normalizer. So we just put normalized term, and this gets reduced before being sent to this tree. Except that nearly works, but it's not enough, because we may also have lemmas that have a pattern, so we expect them to just be automatically triggered by this tree, and that also want to express that some tag have to match some field, has to match some field. And if we put a normalized term here, it will not work because this tree is not able to have a callback to the normalizer when trying to solve a query. And if we just leave that here as it is, it will also not work because in the context, all the instances of tag of field have been normalized upfront by the normalizer. So this tree will probably not be able to prove that precondition because all the instances of tag of field have disappeared. So one trick we can do is simply to have the fact that a tag matches a field as an extra abstract predicate. It's justified using the same function. And now, for every function that checks at normalization time that a tag matches a field, we also provide in Postconditions that field matches tag using the new abstract predicate. And this puts in the environment the fact that a tag matches a field. And then the lemmas that we expect to be automatically triggered can use this abstract fact that should be in the environment. And this solves the problem, and with that we can have, at normalization time, a computation of matching between the tag and the field, and use this fact when running this tree and simultaneously all a bunch of lemmas that we need. And yep, that's it. Thank you, and if you have questions.
I have a backup question, but go ahead, guys.
That's a cool trick. I didn't know about this memoizing the result of normalized term with these abstract predicates. So that's pattern. Did you measure performance improvements as a result of it?
No, I didn't. But yeah, that's something that should be done. So I can say that this trick works. So there is a small caveat that is you basically put that in the environment whenever you check that. But there can be instances where you did not call a function that checks that, and you want that to be true. And if everything was transparent, then this tree will be able to prove it, and it cannot anymore. And in that case, you have to, for example, call explicitly a lemma that asserts that essentially checks that and puts that in the environment. Yep.
What language constructs would you have wished for in either C or one of the other ML-like dialects, that is, for updating the fields and so forth, to make the verifier's job easier? I'm not sure what you mean then. Well, there are a bunch of issues involved, and for example, when you update a field in a struct in a union, when you mutate it, and some of those trade-offs are difficult. If do you update the tag? Do you update all the fields at the same go? I mean, in one go. Do you update the tag and then make sure that you fill all of the other fields with something that's not garbage, for example? So you could imagine maybe there's some language construct that would make all of this happy and easy to use and easy to verify. And
that's a good question. As for language construct, I don't know.
No mutation.
Yep. Yeah. So I guess.
So with no mutation was really useful. You know, COBOL, you can make mutable record fields, and you have 9 lodestar, and that was actually a lifesaver because that means that you cannot observe sharing between record values, meaning that you're free to compile them as C structs that are passed by value, which has been really a boon for MTLS because a lot of the stuff that they wanted to pass, a lot of complex data that they can pass is usually a couple words, and that doesn't have such a big performance impact. So you can have a really trivial compilation scheme with structs as values, as Armel was explaining. So no mutation was actually a great design choice of records for a star.
Yeah. And then I guess the difficulty is as soon as you introduce mutation, you have to use the current design of modified clauses that Tahina is trying to generalize, which specify what has been modified, and then everything that hasn't been modified is unchanged.
As soon as you opt in into the deep embedding, very precise formalization of structs, then you talk about memory mutation, and then you're opting into the whole style of modifies clauses.
Yeah.
So one area that we're probably going to explore is seamlessly blending the easy style that comes with no obligations with the low-level style that comes with more obligations, but also allows you to do more high-tech stuff, so that you don't have, so it's not, contagious, so that you can just keep one data structure in the low-level style and keep mix and matching the two, knowing that you can still rely on the value semantics for things that are not worth the extra effort.
I guess one other thing is that we've kind of taken as a given that we want to compile to C. So the model by which you mutate structs in Union and C is, you know, it is what it is. And like, for better or worse, we're trying to compile to it, so then we have to suffer through this pain of like updating one field and invalidating the other fields.
Right, yeah, that's what I was just thinking. I mean, if you get to dream and you don't have that as a requirement.
But on the one hand, like RML's composite operator that allows you to update the tag and the value at the same time is like a good verification combinator, so that you don't have to do the intermediary state yourself. I had one last question. So at some point in your internship, you did a lot of really great detective work, examining everything all the way down to the Z3 queries to figure out why some proofs were fragile and were not being robust. And that was, really good detective work. And if you had to, think about some tools or some ways that the whole process could have been improved or made easier for the user, what do you wish you had when you did, that really in-depth investigation?
Some things that I wished I had, but it's probably, maybe it's implemented right now, is having a more precise mapping between the FSTAR code and first the SMT queries that are generated. So this is probably easy to do and maybe already done. Yeah, I guess maybe you have a clear idea of the pipeline from FSTAR to the SMT, because at some point I was just trying to bisect on the FSTAR code, just commenting part of it to understand where the problem would come from, because the SMT queries that are generated are big, so you cannot actually read them. So yeah.
Which version of the Z3 Axiom profiler did you use? Mehouse or Clemens or Alexis? Did you use a visual?
I don't know. I googled it and something from the Viper project, I guess.
Oh, okay, so that's Alexis.
Yep. Is there a better one or?
Well, I don't know.
It's the newest one.
There's no total order between the different versions of
Okay.
the Z3 profiler. All right. Well, thanks again, Armel. You did a really great job banging at all these different things and giving us a better understanding of what was happening under the hood. So, thanks.